So, in the first module we did basics, the axioms of probability. In the second module we are just going to get one step ahead. We are going to try and understand what discrete random variables are and how they help us in the context of computing. So, that is going to be the plan for today, to just define what a discrete random variable is and some related notions, independence and expectation. And these are again things that you might have seen or you might be able to relate to, but nevertheless let us try to go through them formally and clearly. So, let us start with a game. I like this game because it's loaded in my favor. So, what you do is you toss a coin, and if you land heads you have to pay me 2 rupees, otherwise I pay you 1 rupee, and clearly a very unfair game, but nevertheless let us go with that. Okay. And so, here if you think about it, in this game the outcomes are not just heads and tails, they are quantities. Let us come to another example where this is closer to computing, which is what we ideally ultimately want to understand. This is a simple code snippet, if you will. You initialize a variable to some 10,000 and you put that into a loop, and each iteration of the loop you check whether L is still greater than 1. Okay. And each time you pick a random number between 1 and L and you assign that value to L. So, now this is a typical code snippet. You will be interested in understanding how many times this while loop executes, and that would tell us something about the running time of the algorithm, and clearly that is of interest to us in computing. Okay. So, this is clearly points us to one thing. It is essential to understand a way to quantify things. Events, in the last module we just thought of events as heads or tails, picking a card from a suite and of cards, so on and so forth. Those are events, but we want to associate the events with some quantities, and we need to do that precisely. And it is not that difficult. We do this in the most straightforward way possible. We define something called a random variable for this. What is a random variable? It's simply a function. Okay, it just takes as input an element in the sample space and outputs a value, a real value for that outcome. So, in other words, if you think of this example shown over here, you have the sample space omega, and all those outcomes that lead to that will, if you evaluate this using the random variable x, the parts that will evaluate to 0, for example, are this. These are all the outcomes that will evaluate to 0, and these are all the outcomes that will evaluate to 1. So, you can see that this is a very natural thing to do. Just each outcome has some quantity associated with it, some real valued quantity associated with it, and we just assign that quantity to that outcome, and you get the real you get the random variable. Okay. This is all a random variable is, and we typically use an uppercase letter to denote random variables. Okay. And often we are interested in discrete random variables, which means that the number of different values that the variable can take is only finite or countably infinite. So, for example, if you go back to this one, is this finite? Yes, it just takes 2 values. What about this? So, here we are interested in the number of iterations. So, this is some experiment that is taking place, this code snippet, execution of this code snippet. Is this finite, the number of iterations? No, why not?
I can keep choosing some number, right?
Yeah, so you can, this can actually be infinite. Why? Because if each time you choose a random number between say 1 and L, if you keep on choosing L, you are not going to reduce the value of L. So, if you think about just possibilities, yes, it is quite possible that you will be at L for as long as you can think of, and that is so essentially this number of iterations is not finite, but it will be countably infinite. Okay. So, now when you think of, yes.
So, if you keep choosing L, will it still be uniformly random?
It's in terms of sample space, yes, that is still a possibility, right? It will not be, it's not a very likely outcome, but even if you think of uniformly at random, it's still with probability 1 over L, you're going to be able to, you'll be choosing L, and that's still a possibility. It's got a positive probability. It's not likely, especially to keep on choosing L, but it's a possibility. Okay, yeah.
Do we keep reducing our sample space every iteration?
It depends on what you mean by your precise understanding of your experiment. So, in this case, the experiment is the entire execution of that code snippet. Okay. So, the sample space is the outcome after the entire code snippet has executed and you are coming out of the while loop. And so, then you can ask, so the sample space really in this case is, did this code snippet execute once or twice or thrice or 4 times, 5 times, and so on. Those are the outcomes. So, you see there are an infinite number of outcomes, and with each of those outcomes we associate the number of iterations as the random variable. Okay. So, there is an infinite number of outcomes possible. That. Back to our notion of random variable, it is important to realize one thing. When you take a random variable x, okay, and you look at you think of it as having a value, say in this case x equal to -1. Immediately what you are thinking of is an event. Why? Because when you say x equal to -1, what you have done is you have isolated your attention to all these outcomes. Those outcomes whose when you take the function x, it leads to a value of -1. Okay. So, going back to our Venn diagram here, it is clear that it is an event. Okay. So, that is something that is important to keep in mind. So, let us come back to our my favorite example, probably not your favorite, but so what do we do here? We have 2 outcomes, either 2. Let us look at it just for the fun of it from my perspective. 2 is what I gain if the coin comes up heads, and I have to give you -1. So, it is a loss from me if the heads the coin outcome is tails, right. So, now one can think of what am I likely to get, so it's a notion that we need to develop. And it's but in this case I am equally likely to both gain 2 rupees and lose 2 rupees. So, it's both of these events, if you will, have equal likelihood. Okay. So, coming back to this loop, let us look at this loop. The number of iterations of the while loop in the code snippet is again a random variable. It can take, as we saw, it can take countably infinite number of values. What is the probability? Remember, these are random events, n equal to 1, n being, let us say here, denoting the number of iterations. What is the probability that n equal to 1? 1 over 10,000. Yeah, with probability 1 over 10,000, you would choose the value of L to be 1. In which case it exits the loop. And what is the slight change that I can do in order to make this have finite outcome? So, let us go back to this. How do I make the sample space finite here?
Let us say stop after some amount of.
That is one way. So, suppose I just want to play with this line. Yes. So, if you choose a uniform random number from 1 to L minus 1, you are certainly going to be decreasing every iteration. So, the number of iterations is not going to exceed 10,000. So, I am going to leave this as a homework. What is the probability that n equals 2? So, in exactly 2 iterations, this loop will exit. Okay. So, that is a little homework for you. Now that we know what a random variable is, let us think of some standard things. So, for example, we already know the notion of independence, and if events can be independent, random variables are closely tied to events. So, the notion of independence should be extendable here as well. So, but we have to be a little bit careful about what we mean by 2 random variables x and y being independent. They will be independent if and only if, now the important thing is this has to hold for all values of x and y. Probability that the random variable x takes this little x value and the random variable y takes this little y value is equal to the probability that random variable x takes little x times the probability that random variable y takes the little value y. This is a very natural definition. It is just that you have to realize that this has to hold for all values of x and y. Okay. So, think of an example this way. So, if you look at the sample space, let us say you divide up the sample space. So, now x equal to 1 is this entire column, okay. X equal to 2 is this entire column, x equal to 3 is this entire column, but y equal to 1, y equal to 3 and y equal to 2 and y equal to 3 are all rows, let us say. So, now if you take any pair, this condition for independence should hold, if you think about it. Okay. So, this is one example where which shows how you can get independence between two random variables, and the notion of mutual independence also extends, and we saw the notion of mutual independence as part of our tutorial last class, right. So, the notion of independence also extends. So, now if you have k random variables, okay, x1 through xk, and for any subset of those k values, there and for any assignable values xi to random variable xi, where the I is in this the chosen index I is in the chosen subset of indices. Okay. This condition has to hold, the independence condition has to hold, and what is that? If you take the intersection of all those events xi equal to xi, okay, variable x, random variable xi equal to the value xi, if you take the intersection of all of those and take the probability of that, that should be equal to the product of the individual probabilities, and this is again direct extension of what we already. Now comes an important topic. So, what is this? We have already alluded to this. A random variable is basically measuring some quantity. So, for example, so in the game that we played, a natural question I can ask is how much do I expect to win? Okay. So, it's if I get lucky, I will get 2 rupees. If I am unlucky, I will lose 2 rupees. Okay. And so, what I can do is I can weight these values. These are my either my gain or my loss. I can weight them by their individual probabilities, and I get the value half. So, that kind of indicates how likely I mean how much I am likely to get. It makes sense, right? If I am lucky, I get 2, otherwise I lose -1. Somewhere in the middle is the half value. So, in general, you can generalize this notion for any random variable. So, consider all the possible values that the random variable can take, and that is denoted by little x over here. And if I just sum them all up, but weighted by their probability. So, obviously, if it can take a value. So going back to our the loop example, it can, yes, I remember I said that it can repeatedly keep choosing 10,000, right, but the probability that it will repeatedly keep choosing 10,000 becomes very, very small. So, you have, when you are computing the expected value, okay, you need to weight the event according or the value of the possible value of the random variable with the probability with which such a value will occur, right. So, when you do that weighting and then you sum up over all possible values that the random variable can take, what you get is the expectation of that random variable x. Okay. So, this is a very natural quantity to study when you think of a random variable. In fact, usually be the first quantity you will want to understand about the random variable. One quick question, will E of x always be a legal value that x can take? No, in fact most of the times it won't. So, for example, in the game that we played, the expectation we calculated was a half, and that is not a legal output at all. It is just a measure of how much I can I am likely to get. Okay. So, let us look at a very simple example. So, here this will be an example for what we are asking for, but also a very important experiment. It is just an experiment where the outcomes are just two, typically called success and failure. It's called a Bernoulli trial. Okay. Any two outcome experiment is a Bernoulli trial. You can assign one the notion of success, the other the notion of failure. Okay. And the typical thing to do is assign a random variable as well, define a random variable as well that takes the value 1 corresponding to success and 0 otherwise. Okay. So, now you can again ask what is the expectation of x. Okay. So, a typical thing would be to generalize and say, look, it is not, it's often people think of Bernoulli trials as fair coin tosses, but the more generally the success can happen with some probability p, and failure should be will occur with probability 1 minus p. Okay. So, what is the expectation? It is very simple, right? You take the individual values. So, 0 comes with the probability weight of 1 minus p, and 1 occurs with probability weight of p. So, when you sum them up, you get p, and this is your expectation of the random variable x. Okay. So, another question you can easily ask is, what would be, so now for a die, the outcome is very clearly a random variable, the number either 1, 2, 3 up to 6, right. So, if you work it out, you are going to get the expectation to be 3.5. Okay, not very difficult to work that out. Can x with countably infinite values have a finite expectation? So, we already looked at one countably infinite sample space and random variable. Can it have a finite expectation? Any thoughts on this? What do you guys think?
I think it can.
Yeah, it can. So, let me introduce one more important random variable. So, here x is the number of tosses. Let us think about a fair coin for now, number of tosses to get the first heads. Okay. And if you think about the sample space, you can actually get tails for an arbitrarily long period of time followed by a heads. So, if you look at the sample space, it is countably infinite. Okay. This is called the geometric random variable, the number of times you have to toss before you get the first heads. But intuitively, when you think about it in a fair coin, if both heads and tails are equally likely, within about 2 rounds you are likely to see a heads. It is a very intuitive statement I am making. The formal proof will be, we will look at it in a short while. Okay. So, this is an example where when you keep you have an infinite sized sample space, countably infinite, but nevertheless the expectation is small. So, we come to the end of this segment. We have introduced the notion of random variables and the notion of expectation, independence of random variables, and so on. We will study a little bit more about expectation in the next segment.